So welcome to the first session. The talk is Naturally Editing Typed Expressions with Holes, given by Cyrus, Omar, and David.
All right. Hey, everyone. Thank you for being here. I'm Cyrus Omar, and this is David. We're going to be putting this talk together. We are three future programming lab people here. So I just started as an assistant professor at the University of Michigan. And we're going to be presenting a progress report, work in progress stuff on user interfaces for editing type expressions with holes. So this is going to be a talk in two parts. I'm going to hand the mic over to David first to talk about natural structure editing in Hazel, and then I'll conclude with a little bit of in-progress work on a mechanism we call live literals in Hazel. So, without further ado.
Hazel is a live functional programming environment with a type-aware structure editor. Let me break this statement down. Hazel is a live functional programming environment. Prior work on the meta theory of Hazel has established this unique invariant that every edit state is statically and dynamically well-defined. That is, every edit state has some well-defined type and can be run to produce a well-defined result. And this is made possible by defining a formal semantics for incomplete programs. So for example, this is an incomplete program, this consisting of a single empty hole with hole index 1. And here's another incomplete program. And this program is incomplete because we're calling map on a function f over here that we have yet to define. But this doesn't stop me from getting useful feedback about the program's runtime behavior. We can still observe the equational behavior of our map implementation for arbitrary f. And if we look over to the cursor, or if we look over to the sidebar on the right, the cursor inspector at the top, it tells me that my variable f is indeed undefined. And the context inspector below tells me what variables are in scope. And if you keep your eyes over on the right sidebar for a second, you'll notice that I get this continuous stream of useful information about the program despite it being incomplete. So this is all well and good. We're super excited to explore this space of interactive programming tools built on top of this liveness invariant. But this is all I'm going to say about the live features of Hazel. And I'm actually going to turn off the live evaluation in order to reduce distractions. So before we get ahead of ourselves, we need to keep in mind the core interface that makes this liveness invariant possible. Hazel is a type-aware structure editor. In order for this liveness invariant to hold, edit states may be incomplete, but they need to be incomplete in a structured way that is recognized by our semantics. And for this, we need a structure editor. Unfortunately, structure editors are known for being hard to use. And if our core interface is hard to use, then it's hard to motivate anyone to use additional tools that are built on top of that hard-to-use interface. So I'd like to tell you about our ongoing efforts to design an efficient and easy-to-use structure editor. In particular, I'll highlight four key mechanisms of our editor. The first is automatic hole insertion. Prior work has already introduced Hazel's hole insertion mechanism. Cyrus spoke about it at the last MWPLS, so I'll keep this part brief. The idea is that Hazel inserts holes automatically to encapsulate incomplete or erroneous parts of the program, whether that's a missing expression, a type inconsistency, or a binding error. And to be clear, these holes are not just part of the UI state, but first-class entities in Hazel's language. So this is Hazel's core language grammar. And we call expressions in Hazel H expressions, where H stands for holes. And note that both empty and non-empty holes, these two terms with the purple hot dog buns, these are built into the syntax. Linear editing affordances. As computer users, we're accustomed to inputting data in a linear fashion, top to bottom, left to right. In Hazel, we can do exactly that. So if I want to extend this infix operator sequence here, I can just type +3. And then if I want to actually bind x, I can go over, create a new line above, and define x. So this was probably totally unremarkable to you as users of text editors. But in the design of structure editors, this is a central design challenge. So to give you a sense of the problem, let's consider a super simple, naive structure editor. In this structure editor, the edit state is a tree. The cursor selects a subtree, as denoted by this green box, and edits are context-free tree transformations on the cursor subtree. So our goal here is, starting from this single node 2, we're going to type out the expression 2 times x plus 3. So I start by typing times. And what that edit did was it created a new node times, took the current cursor subtree and made it the left child, and then moved the cursor over to the right. So that looks good. Let's fill in the hole with x, and then we're going to then press plus. And now this structure isn't what we want. Because edits are context-free tree transformations, we can't rely on operator precedence as we're used to. So we get this association 2 times x plus whole. So to actually get what we want, we'd have to go back. We'd have to then go up to select the entire subtree, then press plus to get the associative structure that we want. So the need to navigate up and down these trees, this clashes with our desire to enter edits linearly. And this tension is well recognized in prior work on structure editor usability. Some structure editors, such as the Cornell Program Synthesizer, simply defer to text editing at leaf expressions and assignment statements. Others apply some sort of online precedence parsing to restructure the tree as it's edited. Our approach is similar in spirit to the latter, but rather than applying edits directly to the language structure, we maintain a separate parallel editing structure that's more amenable to linear editing. On the bottom is our language structure, the H expression grammar that I showed you before. And on top is our editing structure, what we call UH expressions, where the U stands for unassociated. And you can think of these UH expressions as a linearized version of the H expressions that directly encodes the two-dimensional nature of our editing interfaces. So at the top level, we have vertical linearity in the form of lines. And then at the single line expression level, we have horizontal linearity in the form of infix operator sequences. So rather than fighting this tension between linear and tree structures, we simply maintain each structure that's better suited for each purpose. And we can always go from one to another, so we always maintain our well-formedness invariant. So these structures I just showed you are not invisible to the user. Rather, they're shown explicitly through the green signifiers that accompany the cursor. As you can see, these green boxes are updating to reflect the structure here. And there are two parts to these signifiers. The light green shading indicates the smallest containing UH expression node, in this case, the plus operator. And the dark green borders indicate the smallest possible H expression node, in this case, the whole operator sequence. And note how the dark green borders tell me how the sequence has been structured according to the operator precedence. And the green shading tells me what would be affected if, say, I decided to delete the node. We think this visibility into the structure is an important piece of a usable structure editor. And so to illustrate this, let's consider a contemporary structure editor, JetBrains MPS. MPS represents the state-of-the-art in efficient structure editing today, and it's used in many professional development settings. They fully embrace the importance of linear text editing affordances, or linear editing affordances for productivity. And they've developed this interface that feels very close to text editing. But it's still not exactly text editing, and the deviations from users' existing expectations can be surprising. So here's a figure showing some data collected in a user study run, controlled user experiment run by the MPS developers. These two plots show users' perceptions of deletion at the top and selection operations at the bottom. And the bottom plot shows that there's a learning curve to figuring out selection. The novice MPS users, the top row here, they feel that selection can be sort of inaccurate or surprising. But then at the bottom, by the time you become an expert MPS user, they feel pretty good about that. But there still is some learning curve there. And I think the top plot is even more striking. It shows that both novices and experts feel that deletion can be inaccurate. We think the problem here is that MPS presents this linear text-like view, but you still need to know the underlying structures to be able to use it effectively, and it doesn't show you those structures. One thing that I've experienced personally when playing around with MPS is pressing backspace on a delimiter that happens to belong to some large node in my program, and in order to maintain structure, the entire node disappears. And the only way I could have predicted that is by knowing this invisible structure that MPS is not showing me. So we think our tree signifiers are useful not only for learning syntax or for introducing students to a new language, but also for understanding the effects of your edits, even when you become proficient. Finally, I'd like to tell you about a novel mechanism in our design that we call node staging mode. Prior work has paid a lot of attention to the problem of linear entry of infix operator sequences, but there's been a lot less attention paid to similar sort of affordances with other sorts of syntactic constructs. And node staging mode is a mechanism for handling more complex node transformations on these other constructs. So let me show you through a concrete example. Say we're implementing a combat game, and we just implemented this function damage, which takes an enemy attack consisting of the attack type, whether it's a melee attack or not, and a critical hit multiplier. And we only apply the critical hit multiplier if the attack is a melee type. And the return value is the damage points applied to the current player. And now suppose we have the current player's defense score in scope, and we'd like to refactor our damage function so that it takes this defense score into account. And so what we'd like to say is that the current damage calculation is the enemy's attack score, and then we're going to return twice the difference between the enemy's attack score and the current player's defense score. So we start out by creating a new empty line and then defining an attack score variable. The way that Hazel auto-completed this let line isn't exactly what we want. We actually want the case expression in the defining expression here. So if we think about what we would do in the text editing situation, I would backspace on this in delimiter, move down below the case expression, and then re-enter the in to wrap that case expression. Similarly, in Hazel, what we can do is we can hit backspace, and what has happened now is, I should have changed that contrast too. But there is a light blue shading where the green shading is, and the children are highlighted yellow. And here, so in this staging mode provides me a way to shift the delimiters of a node to restructure it according to the sequential structure presented here. So here we see that on the left are these guidelines that tell us what are the viable positions for this in delimiter. Currently it's on this line, but we can also shift it down to wrap the case expression as we want, and then we can press enter to accept. So that looks good. Let's proceed. So now the return value is going to be 2 times attack score minus defense score. And as I so as I pan my caret over this expression, I realize, oh, this isn't actually the association that I want. I forgot to account for the fact that times binds more tightly than minus. So I need to insert a pair of parentheses. So I wrap this, I enter a pair of parentheses here. The autocomplete wraps the smallest node available. And again, this isn't the structure that we want. So again, we can hit backspace on the parentheses. We've entered staging mode. And in this case, now we're getting options to shift horizontally through the infix operator sequence. And so we move the parentheses over, hit accept, and we have our desired refactoring. And one way to think about staging mode is rather than operating on whole trees, we're sort of taking the individual corners of the trees and shifting them in a linear fashion. Again, getting closer to this sort of sequential way of thinking, linearized way of editing programs. So that's the end of my demo. Once again, our goal is to design an efficient and easy-to-use structure editor. We think these 4 aspects of our design are, in combination, get us quite close, and we're continuing to flesh out other parts of the editing experience, such as selection, deletion, et cetera. And we have some promising feedback from a small pilot study that we ran in July, and we plan on running additional user evaluations. And finally, if you're interested in playing around with Hazel, come find me at the poster session. Thanks.
Text-like user interfaces like this, like Emacs, probably a lot of us here sit in front of screens like this all day, then we can bring text-like user interfaces to the structured editing world, right? What I want to talk about is situations where text-like user interfaces aren't great. And we've been thinking about those situations as well. So here's an example. Determine which numbers to put into this code. So we started asking, what if we could fill holes of types like these, like color, for which there is a natural direct manipulation interface, by manipulating an appropriate GUI. And so I started looking at this question way back in 2011, 2012. We have this paper called Active Code Completion, and we implemented a system like this for Eclipse and Java. And so in that system, you could associate these GUIs, which we called palettes, with Java classes like color. And when you brought up the code completion window, you'd see the option to show this interactive palette, and then it would bring up this color chooser. And you could interact with this thing and then press enter, and it would eventually produce the Java code corresponding to the color that you chose. So that color that I showed you was this kind of light blue color. Here's another example. Say you're trying to create a regular expression pattern. That's kind of a confusing thing. The Java regex API is actually quite confusing. And so we built this regex palette using the same mechanism, and you could enter examples, see documentation there on the right, and eventually it would generate the appropriate Java code with all the escape sequences and everything like that. And so briefly, the way we evaluated this was we started with a very large online developer survey of 450 participants. We asked for a bunch of feedback. Then we implemented it based on the feedback from mockups we had developed. And we did a little pilot study. I'm not going to talk about those things in detail, but the result of that work was that we have some good data establishing the usefulness of this kind of mechanism. We solicited a wide variety of use cases for this mechanism. And this mechanism has an extensibility mechanism, so you can associate these UIs with classes of your own. So now, coming back to this work, now that we're working on this Hazel project, we wanted to add a feature like this to Hazel, and in the process, fix some of the issues that remained in the previous mechanism, persistence, compositionality, and liveness. And so I'm going to talk about these things briefly in the context of this new mechanism called live literals, or livelets, in Hazel, which are kind of evolution of this palettes mechanism from the graphite work. So let me start quickly with persistence. So in the previous work, as soon as you were done using this UI, you got Java code and the UI was gone forever. So if you wanted to make any changes, bring it back, it was kind of a pain. There was a kind of hacky mechanism, but it wasn't great. In Hazel, because Hazel's a structure editor, because we're maintaining an AST inside, these UIs, these livelets, are actually expressions. They're part of the syntax tree forever. So they're persistent instead of ephemeral. And so this color chooser, this $color expression, actually is the GUI, and it behaves as a color semantically. So how does that work? This is what a livelet definition looks like from the user's perspective. So we're following a functional model view update model where you have an abstract model of the state of the GUI. Then you have a view and an update function that produce actions, and the actions cause updates to the model, which causes new views to be produced. So that's pretty standard in the functional programming, GUI programming world. For example, Elm uses a very similar model. What's distinct about our approach is that we also have this expand function that its purpose is to take a model and generate the underlying expression AST. So that would take the state of the color chooser, which might consist of the values and all these text boxes and so on, and it would produce the actual color expression. And so, in summary, the way we persist livelets is by just keeping around the model in the AST. We can generate the UI on demand as needed. And the meaning of a livelet expression, like this $color expression, is determined by its expansion, which is produced by running this expand function. So that's persistence. I want to talk about compositionality briefly. I know we're running low on time. The previous mechanism didn't, as soon as you got into a GUI, you were forever in the GUI. You couldn't then nest expressions within GUIs, so you couldn't implement GUIs like this grade table where all of the cells in the table were sub-expressions. In Hazel, you can. So you can put holes inside GUIs, and those holes can contain arbitrary expressions, and you get all of the affordances that David showed you in those sub-expressions. You can also nest, because livelets are themselves expressions, you can nest livelets within other livelets. And so, for example, you could put a slider inside a table in this way. There's a little bit of subtlety about how positioning of the GUI works relative to the expression. We'll talk about that offline if you'd like. And then finally, I'll conclude with talking briefly about liveness. So liveness is really about being able to run parts of your program during editing. And so if you really want to implement Excel as a livelet, you need to be able to not just show the formula for a cell, but its value. So if this variable curve was defined elsewhere, you want to be able to compute its value, the value of this expression, by knowing the environment that this livelet is in. And so we actually rely on this work that we published at PurPL this year to record what's called the hole closure. So we pretend that this GUI is not here, run the program with the hole in it, record the hole closure, and then provide that closure to the livelet implementation. So I'll skip that. So to summarize, this livelets mechanism builds on the palettes mechanism. All the data that we collected there is relevant to our mechanism as well. It's extensible, persistent, compositional, and live. And we're working on doing the theory of this mechanism in AGDA, implementing it, various case studies, and so on. And I'll stop there. You can find out more about the Hazel project from hazel.org, and I'll leave these screenshots from the two parts of the talk up while the two of us take questions.
Right? Like, what's the history of a livelet look like? If I've set something to be royal purple and you think it should be like a little bit more violet,
yep.
What does that look like?
Yeah, so the third member of the FP Lab, who's here, Michael Adams, he's working on that project. So we're thinking basically about if you have multiple replicas of a program that are being evolved by these edit actions that are being performed, and then you want some sort of merge operation, could you define the edit action semantics in a way that the whole system forms what's called a CRDT, a conflict-free replicated data structure. So you need these algebraic properties to hold. The current edit action semantics, the one that was published in PurPL 17, does not have those properties. So we're trying to reformulate the edit action semantics using unique IDs on nodes and a certain way of handling deletion where things are kind of monotonic to handle that. And then basically version control and collaborative editing are both going to be handled through this CRDT collaborative editing mechanism. But that's work in very much progress right now. Yeah.
Other questions? Yeah. This is very, Brian, can you wait for, so I think some of these mics, like that mic is not amping you, so you will have to speak up, but it's for the audio.
Oh, okay, great. So just a minor question about the first part of the talk. In that scenario where you expand the scope of the parentheses, is the only way to hop to the other end of the small expression and delete the closed paren? Or at the moment you inserted the parentheses, was there any way to expand the scope of those parentheses?
Yeah, currently we just have it so that the everything just auto-completes, and then you have to go manually go over to the delimiter you want to shift, and then you hit backspace. But definitely for things like parentheses, it would make sense that if there may be options within the sort of horizontal sequence that maybe it auto enters this staging mode so that you can immediately choose.
Thanks.